My name is John Grimsmo, and in this video I'm going to show you how to turn your Tormac PCNC milling machine into a lathe. Personally, I do have a small CNC lathe that I converted myself from a manual machine, but it is not rigid enough, accurate enough, or reliable enough to do what I'm trying to do for this project. So I'm going to use this bad boy because it's plenty rigid, plenty accurate, and plenty reliable. So real quick, I'm going to explain what I'm trying to make first. The knives that I make use a dowel pin right there, and I'm trying to make a bigger one with a step in it. See on this side over here, that tiny little step, I'm trying to make that so that the base is 0.156 and the step is about 0.163 or something. I'll make a couple of them in different sizes. And I've been having all kinds of problems doing that on my lathe, so I'm going to do it on my mill. And I'm going to be machining 17.4 pH stainless steel, which is a pre-hardened stainless. I think it's about 35 Rockwell. Pretty good stuff. A few months ago I made the tools required to do this operation on the mill, and I was able to make a whole bunch of parts successfully. These are titanium thumb stud and spacers. Both are threaded for 440. So very fine, very small. To give you a size comparison, I mean, there's a USB stick. These things are tiny. These ones are threaded through, and they have a stepped lip on the side. So next up, I'm going to show you the tool that I built a few months ago. Boom. What this is a 1.5 inch by 2 inch by 10 inch piece of steel. Just a steel square bar that I've machined so that it has several different tools and options for tools easily available. Right here I have a 35-degree turning tool. Here is a grooving tool. It's got a full 1/8 inch radius. A little drill bit, I think that's 96 Dow or something. Spot drill. I've got a 1/16 inch grooving tool. And then here I just bought a 55-degree DCMT turning tool. Let's say you want to mount a Tormac TTS tool holder sticking straight up. Or like I did, this is the tension compression tapping head with a little 440 form tap at the top there. So I put that guy right there. If I were to build this again, and I might, but it took a long time because it's a lot of steel to machine, I would do it differently. This is a good starter setup. You get 4 turning tools, 4 TTS tools, and you can shove as many drill bits into it as you can fit anywhere really. I wish I had more turning tool spots, just for the option. And it gets really crowded with the TTS tools, like especially having this guy, because the spindle head has to be able to clear this. To get to the turning tool, it has to be able to fit here. So I wouldn't be able to fit this guy here. It's rusty, so the bore is smaller. Notice all the rust here? Yeah, hence humid environment. I just left it alone for about 2 weeks and it rusted. But yeah, if this guy were here, the spindle head doesn't have enough room to get in here to be able to utilize these tools. So there would be better ways to set this up. So in order to find the center of that hole, the 0, hole, I'm going to be using Tormac's digital touch probe. This is an amazing piece of kit here. I think it's around $200 and it is worth every penny. I know, because I have built my own. It's a pain in the butt. It takes a lot of time. Feel free to do it if you have a lot of time on your hands and if you're pretty smart. But I could not get consistent accuracy with this thing. And I mean, if you don't know what it is, it's called a kinematic point system. I don't know. Think of a tripod, 3 points, and you can tilt up on 3 of the sides. And because of that, it works pretty good for being able to measure anytime this thing gets off center. Okay, so it's a spring-loaded thingy that's pretty much goes back to center every time. And it electrically measures when it's off center. But this thing sticks, it's not concentric, it's hard to adjust. The wires keep breaking off. You know, you can see the wiring gap in there. They keep breaking, I don't know. It was a fun project at the time. I didn't have any money at the time, so I can't complain that I did it, but now that I can actually afford one of these, worth every penny. So anyway, let's use this. And then I'm just going to use the jog pendant to manually find the hole. So I don't need to be centered in the hole, I just need to be in the hole and not touching the walls. Done. Interesting. I ordered 1/4 inch stuff. I tried to put it into the collet. It doesn't fit. This stuff is 0.281. 1/4 inch is 0.250. That's big. That's really big. Weird. I ordered 1/4 inch. I'm surprised that's even a size 281. It looks really nicely round and circular. I don't know, that's weird. Bummer, dude. I was totally planning on using this. I think I might actually have to use a drill chuck. Ew. So a drill chuck is attached to the tool holder with a taper. I think this one's called a JT33. No, this is a JT2 taper. So, you know, taper. And here's the tool holder, and you see this gap right here, right where my eyes are. So the tool holder has a taper, and then the drill chuck has a taper, and it's kind of a shrink fit together, or you pound them together or whatever. If, like, a drill chuck works great with loads going this way, but any loads that go this way can cause the thing to flex and that taper to fail. And what can also happen is the little nub can totally break off. I haven't done it myself, but I've seen it done. That's also why you never put an end mill in a drill chuck and expect to mill like that, because that can break. However, I've done a lot of that. Never had a problem. Not that I'm recommending it, but I'm saying it, I've done it. However, when turning, like if I put my workpiece in the drill chuck and organize my tool paths so that they're not going like this, but they're mostly all going like that, or you know, if my finger is the turning tool, then it goes bzz, 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 then that should work. Except for parting, which has to go in like that, but I think the cut load will be so light that it's not going to be an issue. So, although I was going to use the collet, because I've used that before and it works awesome, I'm kind of stuck using a drill chuck with this stupid size. Weird. Now, allow myself to explain myself. If you're able to follow what I'm talking about here, and you're kind of a machinist to know how things work, you may be asking yourself, how do I set each tool offset so that the machine knows where they are? In a milling machine and in Mach 3 Mill, which is the control software that runs this whole thing, each tool change only has one value, and that's the length value, because they're all going to be on this center line. None of them are going to be left or right from the center line. So all they need to know is how long the tool is. Whereas in a lathe, you have left and right and in and out offsets to deal with. Here you don't. So how I do it, there might be other ways to do it, but I use what's called a G52 offset. And here's the center line. I can do calculations and know that this tool has a G52 offset of, I don't know what it is off the top of my head, but it's something like 6.11 inches X. Okay, so it's that far away from center line. And from here, if I guesstimate that out that way, to the tip of the tool, the Y offset is 1.04. That's a random guess, but so G52 offset would be, it would say X 6.1, Y I think negative 1.4, whatever it happens to be. And then Z from this surface down to this surface is a tiny bit, eighth of an inch or something. So you do a bunch of test cuts and you figure out what the offset is for every single tool, or you use the touch probe to touch off the tip and the side and do some quick calculations. That works too. Now, one thing to note about working with a milling machine as a lathe, there are some differences. The differences are, if you're used to working with a lathe, normally, like let's say this is 1 inch diameter, which it is. A lathe knows to multiply the radius times 2, which equals your diameter. So you zero the tool here, and you call that 1 inch. Okay, let me see if I can. This is how you would look at it on a lathe. Okay, so you would call that 1 inch, and then as you're cutting towards the center line, it calls the center line 0. Now it only traveled half of an inch, but it knows that this is 1 inch and this is 0. So that half inch of travel, they call it 1 inch because it measures in a diametrical value, diameter value. Whereas working on the Tormac or any milling machine as a lathe, you have to know that this is only half inch of travel and you have to call it half an inch. So every value you do is divided by half. So if I'm going to face off this 1 inch piece, I start at 0.5 and I go to 0. I think. Yeah, that would work. And if you have a CAM program that develops fancy curvy profiles or whatever, you're probably going to have to manually go in and divide every X value by 2. And I think you have to make them all negative, but that might depend on if the tool's on the left side or the right side. The cool thing about lathe work is for simple stuff, once you have some experience, you can literally write the code by hand. You can just go, okay, X0, blah, 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 G3, curve, blah, 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 turn. I want this diameter, blah, blah, blah. So my goal is I want it 160 diameter in one part, so I need to divide that by 2, that's 0.08 inch. So in the code I'm going to have to write 0.08 inch. For those who are interested, I just wanted to give a real quick run through of the code. Because it's really funny, it doesn't really show up right in the program. I mean, you can see all the turning passes there, but they don't look the way they're supposed to look. But here's the code, just a bunch of notes that are irrelevant. I'm calling the rod tool 126 for no reason, really. Move up, move to the offset of the current tool, speed 100, turn the spindle on, no coolant for this run. Title of what I'm doing. Here's the G52 offset. So the tool is 6.433 over and 0.482 front to back, and then negative 395 down. And then just rapid moves, feed rate, some facing, some turning, finish pass a little bit slower. These are guesses as far as speeds and feeds. Blah blah blah. I wrote all this by hand. It took me about 25 minutes or so, maybe more. And then change the parting tool. It cancels the G52 offset right here, moves up a bunch, moves to the new G52 offset for the parting tool, which is similar but slightly different. Feed rate, blah blah blah, parting. And for the parting, I'm going in, out, in, out, in, out. So I'm kind of pecking at it. And this right here is a little chamfer just to break the edge. We'll see if it works. And that's it. And then make sure to cancel the code at the end, the G52. Turn the spindle off, go up, you're done. Here we go! Oh, that sounds good. Cool. Working so far. No. Dang it. Didn't like that. Not exactly sure what's going on, but I think just visually it looks like it's not centered Y. You know what? These Norsemans are so light, it's easy to carry 9 of them at a time. Check this out. 1. I finally made my first successful part. Okay, the dimensions are not exactly where I need them to be. You can see the right side step is a little bit shorter than the left side step, so I just got to tweak some dimensions that way. And also the step on the right side is 1/1000th of an inch smaller than the step on the left side. And you can actually kind of see it on the video. Alright, this is pretty cool to watch. Now that I don't have such a long overhang, the part doesn't flex so much and it produces a really nice clean cut. Just perfect. Well, for my second part that I made, this is nearly perfect. Let's see what the length is. I haven't measured yet. Length is 310. It's supposed to be 315, so it's still 5 thou short. And that might be an offset difference between the parting tool and the turning tool, so I'll look into that. But the shortness doesn't bother me at all. As far as diameter, it's supposed to be 1565 pretty much. 1565. So as a hobby machinist, I've always used this to measure everything. You can see it's flashing. It's really annoying. When the battery gets low, it starts to flash. So I just haven't gotten around to replacing the battery yet. It still works. This exact tool I've had for like 6 or 7 years, and I've used this same one for everything pretty much. I mean, these digital calipers are great. They're like 20 bucks. They're fairly accurate. But as I've become a better machinist, I'm learning that some of the more manual tools, like this micrometer, are way more accurate and more repeatable. So I don't know if I need to really show much more. You've seen how the turning center works, how I use the tools and the offsets and G52 and all that. You know, this code is how I wrote it. All written by hand. That's kind of the annoying thing about turning on a mill, is I'd say I'm decently okay at handwriting lathe code. You know, I'm self-taught and everything, so I kind of figured it out, but you know, I can sit down and I can just type out lathe code. But it's still kind of a pain, because not only do you have to divide all the X measurements by half, but there's other things you have to figure out because it's on a mill. And all the offsets get really confusing between all the different tool offsets. But you figured out. I mean, obviously I was able to make an awesome part there. And that's pretty much all there is to it. To wrap up this video, I'm going to show some old footage of using the mill, like I talked about before, to make those titanium thumb studs and spacers. It's pretty cool because there's a threading operation in the middle. Alright, so it's much later, and I finally got this down to a science. Quick tip that I wanted to get down on video before I forget about it. The workpiece, like the titanium rod, was actually slipping up into the collet while I was trying to tap. So when it would go down, let's see if I can see there. When it would move down towards the tapping head, the rod would just kind of shove back up into the thing, and it was driving me nuts for like 45 minutes why every single part was a different thickness. It's supposed to be 135, some of them were 1.3, some of them were 1.19, 1.15, like all over the place. And it turns out it was slipping up, so I just had to tighten the bolt on the drawbar and give it more clamping pressure. Now, it works great. So to wrap up this video, turning on a mill is kind of a pain in the butt to set up, but once it's set up, oh, it's so nice. I've just made about 12 parts in no time, so it is worth it, especially if you don't have a lathe or if your lathe sucks like mine does. So there you have it, guys. It's worth doing. Thanks for watching. Bye.